I'm going to show a nice proof, actually a very nice proof, that shows that E is an irrational number. I did not come up with this proof, and it is just simply a beautiful proof. One of the nicest proofs I've seen in a long time. So what we're going to do is we're going to start off with the definition of E. E is known to be 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial forever and ever. Now we're going to define partial sum of E. It's 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial all the way up to 1 over n factorial. E minus s sub n is gonna be positive because you're adding all these positive numbers, an infinite number of them, but then you're only taking away a finite number of those terms. There's gonna be something left over, and what's gonna be left over is, well, Sn stopped at 1 over n factorial. So when you subtract it, like I said, E is going to have more terms. It's going to have 1 over n plus 1 factorial plus 1 over n plus 2 factorial plus 1 over n plus 3 factorial forever and ever. So 0 is going to be less than or is less than E minus S sub n. Now from here I want to factor out 1 over n plus 1 factorial. And what's going to be left is 1 plus 1 over. Now here I end at n plus 1, but here is n plus 2. So I have to have the n plus 2 plus the next term with the 1 over n factored out. This goes up to n plus 3 factorial, but I only have up to n plus 1 factorial. That is, or n plus 1. So I have to have n plus 2 times n plus 3. This is going to happen forever. So 0 is less than E minus S sub n. Now I'm going to make the right hand side bigger. I'm going to keep the 1 over n plus 1 factorial. I'm even going to keep the 1, but everything else I'm going to make smaller. Instead of this, I'm going to make the denominator smaller, which makes the fraction bigger. Over here, I have the 1, but instead of n plus 2, I'm going to put n plus 1 times, instead of n plus 3, another n plus 1. So I'm going to have n plus 1 squared in the bottom. And the next term, I'm going to make smaller. I'm going to put 1 over n plus 3 cubed. Dot, dot, dot. Okay. Now, so let's write this down. E0 is less than E minus S sub n, which is less than 1 over n plus 1 factorial times what's in the brackets. So what's in the brackets is a geometric series where R is n plus 1. Sorry, 1 over n plus 1. So I'm going to get 1 over 1 minus R. which is 1 over n plus 1. And if I multiply the top by n plus 1 and the bottom by n plus 1, which in effect is multiplying by 1, which is allowed, I get less than 1 over n plus 1 factorial. 1 times n plus 1 is n plus 1 over, like we just said, 1 times n plus 1 is n plus 1 minus that product is just 1. So, a couple of things happen here. 0 is less than e minus s sub n, which is less than n plus 1. I kill on the top, and I kill off one factor of n plus 1 in the bottom, and I will be left with n factorial. And if you have 1 and you add 1, and you take away 1, you just have the n. So all that survived on top is 1 over n factorial times n. Now, I'm going to multiply all three sides by n factorial, which is positive. This is true for everything I've done is true for any n equal to 1, 2, 3, etc. So when I multiply 0 by n factorial, it's 0, of course. Thinking about the next term, how when I multiply this by n factorial, I'm going to have to write it. And the left side, the right side, is 1 over n. Okay. Notice, if n is more than 1, this will be less than 1. For the most part, this will be less than 1. But we're actually going to show that for any n that we're going to use, that it's less than 1. Okay. So this is a pretty key step. This is pretty key. Now, I'm going to say, suppose E is rational. I'm going to do the opposite of what we want to prove. And then, now either E is rational or it's irrational. If we get a contradiction that is rational, then it must be irrational. So suppose E is rational. That is, E is equal to P over Q, where P and Q are positive, kind of clear that they're going to be positive. I guess they both can be negative, but let's say they're positive integers. This E is positive. The bottom is not 0, and P over Q is in reduced form. Now, the only thing we said for the entire proof that may not be true is what we're supposing. Maybe that's wrong. Maybe it isn't wrong. Let's get our hands dirty and find out. So now, let us write down this equation. What's the new, or another way, or the new way of writing E? So we have 0 is less than n factorial times P over Q minus n factorial times Sn. Okay? Now, some syndrome, which is less than 1 over n. Rearranging things, I have 0 is less than n factorial over Q times P minus n factorial times this, which is 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial, all the way up to 1 over n factorial, which is still less than 1 over n. But now I am going to choose n in a clever way. I am going to choose n to be bigger than q. Now remember, q is 1 or 2 or 3, so this implies that n is bigger than 1, which is going to imply that 1 over n is less than 1. So, like I said, this piece here that is less than 1 over n is less than 1. So let's write that. So we have that 0, so let's write it right here. We have that 0 is less than n factorial over q times p minus, I'm even going to distribute. Okay, so I get n factorial times 1, which is n factorial times another 1, and then n factorial over 2 factorial, and then n factorial over 3 factorial, all the way up to n factorial over n factorial. And wish I had just a drop more room, but remember, this is less than 1 over n, which is less than 1. Whoa, wait a minute. This piece, whatever it is, it's between 0 and 1 and not one of the endpoints. So, remember, that was just e minus or Sn. E minus Sn is not, it's not an integer. It's between 0 and 1. It's not an integer. Okay, so what's in blue here is not an integer. Okay, this is that. It's not an integer. Okay, wonderful. So now let us look at what's in that blue box more carefully. N factorial over q times p minus n factorial plus n factorial plus n factorial over 2 factorial plus n factorial over 3 factorial, all the way up to finally when the denominator is as big as the numerator. It's n factorial in the bottom. All of these numbers, 2, 3, they're all less than n. Only the last one are we taking a factorial of n. Never more. Okay, now here is where it comes together. N factorial is 1 times 2 times 3, all the way up to n, all the way up to times n. But let's look at it carefully. N is bigger than q. That is, q is less than n. That is somewhere in between 1 and q, 1 and n, you're gonna have a factor of q. You're gonna have a factor of q. And this q is gonna go into it. That is, this here is an integer. And we are multiplying it by p. By definition, p is an integer. And we are subtracting an integer plus an integer. And likewise, since 2 is less than n, 2 factorial goes into n factorial evenly. Same with 3 factorial. Same with all the others. The last time it goes in, one time. But the bottom line is, when you add all those integers, you know what you get? You get an integer. If you remember when you were in grammar school, and you never even heard about integers, an integer times an integer was always an integer. 7 times 9 was never, 42 thirds. It was always an integer. And if you have an integer and you take away an integer, you get another integer. Okay, so that means that all of this is an integer. But all of that is e minus Sn. And we just said a moment ago that e minus Sn is not an integer. That's a contradiction. Okay? That is our contradiction. Oops. That's our contradiction. Right here. Contradiction. We can have e minus Sn being both an integer and not an integer. So, e minus Sn, okay, so e is not rational, because when I assumed that e is rational, I suppose that it was rational, I got a contradiction. I got this mess is not an integer, and it is an integer. And that only came because we assumed that e is not rational. So if that's wrong, then e is irrational. Okay? If you're not rational, you're irrational. If you're irrational, you're not rational. Here is the